Bene, bene. A posto.
Adesso vediamo.
No, come no? Guarda, è generale, vorrebbe essere. No, dai, è abbastanza introduttivo, più introduttivo. Tu non scegli all'altro seminario che aveva fatto in dipartimento? Vabbè, comunque era, questo è un po' più introduttivo, quello era un po' più tecnico. Anch'io ho fatto lezione quando ho fatto
Messaggio,
da lunedì cominciamo.
probabilmente tocchi già subito lunedì, adesso vedo
Ci sono.
Mauro con Emanuele.
Bene.
Hello, welcome everybody. So we have a pleasure today to have this seminar, part of a breakthrough in material science given by Professor Silvia Picozzi. So Silvia joined our department last year, and she's coming from center-south of Italy research-wise. So she got her laurea in L'Aquila, then PhD in material science. So she joined the correct department and in University of Camerino, and then she had her career all in, before coming here, all in the CNR in Chieti lately, where she was, director of research, also director of the institute, Spin Institute. So she's one of the most known physicists, theoretical physicists studying spins, ferroelectricity, an H index of above 70. So we are really happy to have her in our department. And today she's going to talk about spins and electric dipoles, modeling, and microscopic understanding.
Yeah, thanks so much, Francesco, for the kind introduction, and thank you all for joining. So today I'm gonna tell you a bit about my field of research. Given the audience that I'm very happy to see there are many students, so I'll mostly introduce the ingredients that I need to then show you in the last part the research results. Before starting, let me thank my collaborator, long-term collaborator, Paolo Barone, Andrea Droghetti, Danila Moroso, and Serjan Stavric, who contributed basically to the results that I will show you today. So the topic of the seminar is, this class of material, namely ferromagnets, ferroelectrics, and their, kind of interplay, namely multiferroic. And these are all so-called functional material, which is belong to a material science department, as you know. And so the concept of having a material that has a function is particularly important for us. And the definition is not probably uniquely given, but certainly a material that can be controlled, as in a ferromagnet or a ferroelectric, by an external stimulus, like an electric field or a magnetic field, is certainly something that, a material that can be used. So they are, paradigmatic example of functional materials. So my point of view, as outlined in the title, is of course I'm starting with the phenomenology, so a material that has a certain, shows some kind of properties, but then my field of action, let's say, is looking for the microscopic mechanism. So really, in terms of which is the electronic structure that underlies this certain phenomena. And so we used an approach which is fully first principle. So we don't need any experimental data to be input, and this is basically density functional theory. I would also like to outline the role of symmetry in the field. So explaining or discovering also microscopic mechanism is very much supported by symmetry. So this helps you to predict whether mechanism is allowed or not. So I had the privilege for long to collaborate with a professor, very smart professor, Professor Daniel Komsky, and he used to say that if symmetry predicts some mechanism, it will happen. Even if it hasn't been, observed in a material, then it just means that probably we didn't, know where to search or what to search for. So if symmetry tells you that something is allowed, then it's likely that it will happen. So in terms of microscopic mechanism, the support of symmetry is really helpful for us. And then in the last part, I will show you an example of application of multiferroicity and microscopic mechanism in a class of material which is very popular nowadays, so this two-dimensional quantum material. So again, the emphasis is on mechanism. And I thought for the sake of being as general as possible, I won't have many equations, right? I'll try more to give you, let's say, flavor of what happens and what is the role of different ingredients. I'm a theorist, and I won't show experiments or very little, and I will not show at all application. Although I'll mention something during the seminar. So I promised to tell you something about ferromagnetism and ferroelectricity. So probably you're familiar with, piece of iron being magnetic. So a magnetic material is what? Is a material that shows the ordering of magnetic dipoles below a certain so-called Curie temperature. So the analogy with a ferroelectric material is in the ordering of something. So while here in a ferromagnet, the magnetic dipole order, in a ferroelectric material, it's the electric dipole that order. And here I show probably the most known ferroelectric material, barium titanate. So that's one connection. And so these are examples of phase transitions. So you're probably all familiar with, phase transition of water to ice. So I have a highly symmetric disorder phase at high temperature, and then below a certain ordering temperature, then the molecules of water orders in a kind of crystalline arrangement. And so you can think of these to be applied to spins as well. So I have, disordered spin at very high temperature, and then as I cool, then my spin order. And so as a result, I get an ordering parameter, which in the case of ferromagnetic material is magnetization. So you see this order parameter rising below certain critical temperature. And so you can basically extend this approach to ferroelectrics. So you can just substitute magnetization with polarization, which is the magnetic, so it was magnetic magnetization per volume. And so you can think that in a ferroelectric you have polarization, which is the electric dipole per volume. So it's a sum average over all the electric dipoles. So instead of ordering of spins, you have ordering of electric dipole. But other than that, the phenomenology is kind of similar. Another, connection or analogy is that they both are bistable material. So not only you need to have a certain dipole moment or a certain magnetization, but you also need to be able to switch it, right? You need to have a plus p state and a minus p state, or a plus m state and a minus m state. And so typically your energy curve, total energy curve, as a function of a generalized coordinate has a typical double well with this, plus p and minus p state to be degenerate. So you might wonder, since p up and p down are exactly degenerate, how the material chooses whether it wants to be up or down, because they're degenerate. And so think of it like, being sit on a round table, and you have like the cup. You have a cup on the left and a cup on the right. And how do you choose that? You don't know. It's exactly the same. But once, one person starts picking the right cup, then everybody will pick the right cup. And so you basically develop in the material, you have a kind of domain, so a region in which all your dipoles are ordered in the same way. Another analogy is that both ferroelectrics and ferromagnets show a kind of hysteresis cycle. So in the MH phase space, you have a kind of hysteresis, the meaning of which is that the area enclosed by this hysteresis cycle tells you the energy stored in a material or involved in the reversal of the order parameter. So there are many analogies, but of course there are many differences, right? The first one is exactly the microscopic one. So I told you that in the ferromagnetic or magnetic material is the spins that order, but in a ferroelectric is not like this. And so typically, in some material, you really have like a disorder moments that or electric moment that orders. But in inorganic compound, you often have a displacive transition. So what happens microscopically is that, for example, in barium titanate, you have a titanium at the center of an octahedral cage, and then titanium displaces versus, this lower apical oxygen or upper apical oxygen. And so depending on the kind of displacement, you will get a total energy curve showing the double well, and correspondingly your order parameter polarization will switch from positive to negative. So you can immediately see that, of course, the microscopic origin of a ferroelectric has nothing to do with the ordering of spins. And so ferroelectric and ferromagnet, along with ferroelastics, which are material that choose a spontaneous deformation below certain ordering temperature, they are generally called ferroic. And so multiferroic is a material that shows ferroelectricity and ferromagnetism at the same time. often people confuse, or you hear, multiferroids in connection to magnetoelectrics. And so what is the difference? So multiferroids are materials that are spontaneously a magnetization or a polarization. Whereas a magnetoelectric is a material in which you control ferroelectric polarization with a magnetic field or magnetization with an electric field. So in addition to having, in a standard magnetic field, you have an MH hysteresis cycle or a PE hysteresis cycle in a ferroelectric. In a magnetoelectric, you have a kind of, crossed hysteresis cycle, so you have P versus H or M versus E. So magnetoelectric is something in which you can control one property with the non-conjugate fields. And that is particularly helpful, especially the idea or the dream is to control spin degrees of freedom with an electric field. That is much easier. Applying an electric field is much easier than applying a magnetic field. So in particular, this hysteresis cycle is particularly, searched for. And multiferroics are, in general, complex material. So again, the definition of complex material is vague. So they might be thought to be complex just because, we don't understand them well. That is a safe definition. But you can also define a complex material by, a material having more than 1 degrees of freedom to be active. So in many of these magnetoelectric or multiferroid material, you have, spin degrees of freedom, for sure, because they're magnetic, and lattice degrees of freedom because they are ferroelectric, but then often, and also charged, because there's a dipole, but also they are kind of strongly interacting. So also the orbital degrees of freedom are involved. And they're certainly belonging to the class of, which is very popular nowadays, is quantum material. So certainly spin is a quantum property, and we cannot, not consider multiferroic among the class of quantum material. So I told you that, there's no application in this seminar involved, but of course, both ferroelectrics and ferromagnets are widely used material, especially because every ferroelectric is a piezoelectric. So piezoelectric means, that I apply an electric field and my material is kind of compressed or strained, and vice versa. I strain a material and the polarization develops. And so piezoelectric are strongly used for transducer and actuators and other application. Also, ferromagnets are at the center of so-called spintronics, so the electronic based on spin. But again, my field is not so much related to application. So my field is more connected to the kind of complex and exotic magnetic order that a material can show. So nature is really rich, and I'm still, surprised by how rich can, nature be. So by rich, I means that I not only have spin, pointing in all the same direction, but also you can find anti-ferromagnet, which just means that, in different sublattices, I have spin pointing in one direction in just the opposite direction. And I can also have free magnet, in which I have, one kind of magnetic atom pointing in one direction and another kind of magnetic atom with a different magnetic moment pointing in the opposite direction. So these are all kind of collinear state. But what is fascinating is that it can also get non-collinear, kind of spiral. So from side to side, the direction of magnetic moment changes. And they can also go non-coplanar. So they can go, for example, they can point along the center of a tetrahedra, or also you can have, even complex, more complex, and so-called topologically non-trivial spin configuration like a skyrmion and anti-skyrmion. And you really find this, example of complex ordering in material. And as you can imagine, it's, the understanding why they, adopt this complex ordering is, is an intriguing question. So about antiferromagnets, because most of the things I will show are antiferromagnets, I wanted to point out a quotation from the Nobel lecture of Louis Néel. So Louis Néel got, Nobel Prize for antiferromagnetism in 1970 for his, prediction of, much earlier prediction of antiferromagnetism. And so he said that a large number of antiferromagnetic material is now known. These are general compounds of transition metal containing oxygen or sulfur. They are extremely interesting from the theoretical viewpoint, but they don't seem to have any application. So at that time, it was completely unclear whether, antiferromagnet could ever be, applied. Now think of what happened today. In your hard disk, whatever, in every computer that you have a redhead sensor, and the redhead actually, has a sensor which is magnetic. It's so-called spin valve. So spin valve means that you have your two magnetic layer with here, two magnetic layer with a spacer in between. And then you pass with your spin valve sensor over your hard disk where you have your magnetic information stored. And then this upper, let's say, ferromagnetic sensor just lines up with the local region in which you have a magnetization pointing left or right. And then depending on whether the two layers are lined up or anti-aligned, you have a certain different current. And so you basically need to have a free layer which just follows the direction of the magnetic beat that you're sensing, but this other one needs to be fixed. And the way you clamp it is through connection with antiferromagnetic material, with a mechanism called exchange bias. So in every hard disk, you have an antiferromagnet. Although a Nobel laureate said that, there wouldn't be any application. Not because Néel was, of course, he was a smart guy, but just to say that sometimes we do research for which we don't immediately see the application, right? They will come, in ages. And so in this sense, I would like to emphasize the importance of basic research. We don't need necessarily to just work on, research that has immediate application, but we can, discover mechanisms that maybe, one day will find, huge application. Okay, so to get to the microscopic mechanism that I will mostly discuss, kind of, simple symmetry consideration. What is inversion symmetry? So inversion symmetry is what I take, a reference center and then just invert the coordinate. So the molecule or octahedral cage like this will be coming, inversion symmetry connected. So certainly a dipole lacks inversion symmetry, right? I have a plus P, plus Q charge and a minus Q charge. So any kind of ferroelectric material needs to break inversion symmetry. And so what I showed you before, like plus P and minus P, are inversion symmetry partners. That is obvious, like you move atoms, and then you get, plus P and minus P state. Less obvious is how you break inversion symmetry magnets. So assume now you have a spiral. So spiral means what? That these are the lattice sites, like iron and manganese, And then your spin moment is, rotating from side to side. So you will get a spiral. This is, I don't know, clockwise, counterclockwise. Right? It's rotating like this. Now, let's apply inversion symmetry. Inversion symmetry means that I need to break, this atom from here to here, from here to here, from here to here. And so you will immediately see that, it's not the same. So certainly the inversion symmetry is broken. And actually a spiral that was left-handed by inversion symmetry becomes right-handed. So these are inversion symmetry partner are kind of opposite, and so you basically switch the so-called chirality of spin. So you have a chirality from the upper, let's say, counterclockwise spiral, which becomes clockwise in the right-handed. So certainly a spiral, although the atoms themselves would keep inversion symmetry, right? Because the red atom is a red atom here, a red atom is a red atom here. But once you include spin degrees of freedom, then you break inversion symmetry. And so in magnet and in non-collinear magnet, you have an additional way to break inversion symmetry. And so it was realized like back, I don't know, 20 years ago, that actually a spiral breaks inversion symmetry, and so you satisfy the prerequisite of having a ferroelectric material. And it was discovered that a spin spiral not only breaks inversion symmetry, but also breaks it in a polar way. So you have polarization developing from the spin spiral ordering. And that was proved in a class of material called manganites. So manganites order at temperature which are, I don't know, 30 Kelvin. And when they magnetically order, so this is the Néel ordering temperature, then you have the ferroelectric polarization popping up, which means that the two kinds of order, the electric one, of which you're measuring the order parameter, and the magnetic one, of which you're measuring the ordering temperature, they are connected. They share the same microscopic origin. It's the spin ordering itself that breaks inversion symmetry and gives rise to polarization. And so this is basically, a slide that I showed for the ERC interview. So that is my activity for many years. So you have ferroelectricity breaking inversion symmetry. And in standard ferroelectric, it's basically the ions that break inversion symmetry. And you have a so-called proper ferroelectricity. Proper means that you have ferroelectric polarization, which is the only order parameter of the transition. But you can choose an alternative way. So you can choose the electronic degrees of freedom to break inversion symmetry. So in this case, ferroelectricity is improper. So the primary phase transition is driven by electronic degrees of freedom. It's just that as a byproduct, you break inversion symmetry and polarization will pop up. And so electronic degrees of freedom are several, not only spins. Spin degrees of freedom is certainly there, but also you can think about breaking inversion symmetry with charge order. So you have a certain charge ordering developing, and this breaks inversion symmetry and gives rise to polarization. Or the orbital order. So you have some orbital ordering developing below certain transition, and this will give rise to ferroelectricity. And so, as I said, we worked for several years on a project called breaking inversion symmetry in magnets, understand via theory. So we basically worked on the microscopic discovery and characterization of material that would show this kind of phenomenology. So we discovered some where ferroelectricity is driven by spin, some which where ferroelectricity is driven by charge ordering, and some where it's the connection between charge and spin that give rise to ferroelectric polarization. So the question is, why would you do that? So what is the nice thing about having a ferroelectric polarization driven by electronic degrees of freedom compared to standard ferroelectric, right? And so there are two advantages, maybe. The first is that in barium titanate you move atoms, right? So once you cycle and cycle in a ferroelectric loop, like 10,000 times, then your hysteresis cycle will degrade. So you move atoms, and then at some point the material kind of breaks or defects develops. So you have something called fatigue. So after many cycles, the hysteresis cycle and the performances in general of the ferroelectric will be reduced, kind of degraded. But if you move electron, these are much, this is much easier, right? You don't need to fatigue should be, much less problematic, right? Switching electron, or moving electron, or controlling spin is not like, moving atoms. Second thing is that the connection, so the magnetoelectric coupling is much stronger if you have ferroelectricity driven by spin degrees of freedom, right? Because they share, basically, ferroelectricity and magnetism share the same macroscopic origin. You cannot have ferroelectricity without magnetism, and vice versa. So once magnetism develops, ferroelectricity is bound to it. So the coupling and the origin is exactly the same one. So they're tightly connected. The disadvantage is that the ordering temperature are usually low. So in this kind of complex material, the ordering temperature are generally, low. We discovered one which is like 200 Kelvin, which is, our peak. But definitely it's a low temperature field. Okay, so that was my activity, some, years ago. And then in a few years back, we started to work on 2D materials. So this, just a slide of a couple of slides to introduce the class of material. So these are, one or few atom thick system in which the layer, so you have a layer of, graphene or molybdenum bisulfide, which is held to the other layer, neighboring layer, by weak van der Waals forces. And so they have an extended range of properties, but the nice thing is that you can stack them very easily. So people say you can play Lego with this 2D material. And so you can stack them without having to bother about, the lattice matching and kind of interdiffusion that, of course, people have to take into account when they work with, inorganic or like 3D material. So you can really stack. And not only stack, you can also twist and get new properties. You can slide and get new properties. You can bend. People are creating nanotubes of chromium-I3. And so you can think that, by this, structural modification, your property will change. So in addition to having certain property deriving from the kind of, chemical constituents and structural local arrangement, then you can get many more properties by playing with the structure, twisting or stacking or sliding. So they are really kind of flexible class of material. So, as I told you, this 2D boom started with graphene. But then in 2016 or 17, people discovered that actually even a monolayer or a few layer of some magnetic crystal would occur. So for paradigmatic cases are chromium-I3 and chromium-germanium telluride. And so people would discover that actually there is certain ordering that emerges below a certain temperature. And so there was a question, right? Because, I mean, what people thought was based on the so-called Mermin-Wagner theorem. So the Mermin-Wagner theorem says what? That if I have my spins, and my spins are kind of isotropic in space, then in dimension lower than 3, you cannot have long-range ordering developing at all. And so the discovery of having magnetism itself in a 2D material was a kind of, surprise. But of course, the Mermin-Wagner theorem is certainly valid, but it assumes that the spin are isotropic, right? They can, behave in the same way depending on where they're pointing to. And it neglects anisotropic effects. So like, for example, from the microscopic point of view, you have spin-orbit coupling in material, so the link between, angular momentum and spin momentum, which pins the direction of your spin, for out of plane or in plane, but anyway, they're not isotropic. So the breaking of isotropy is what, allows the emergence of magnetic ordering in this like monolayer. And they are a rich class of material. They are chemically rich. They are, binaries, ternary, chalcogenides, halides. From the crystalline point of view, you have triangular and honeycomb. From the electric point of view, they are also rich. You can find metallic ones, you can find insulating ones. And of course, they are rich from the magnetic point of view. So you can find those having magnetization out of plane and in plane, collinear, non-collinear, non-coplanar, ferromagnet, antiferromagnet. So it's really a nice class of material to play with. And so I wanted to show you now some results and tell you a tale of nickel-I2, which is one of my favorite material. And so the first question I want to ask is whether this 2D magnet can show exotic spin texture. So I told you that nature is rich, but it's also true that not conventionally you find complex spin texture. So can you have them in 2D magnet? Okay, so 2D magnet are, okay, you need to, sorry, I think I need some water. Okay, wait a second. Okay, let me try. No, I cannot try, sorry. Or maybe I can try. Let's see. You basically we built a monolayer of nickel-I2. So nickel-I2 has nickel, which is an atom with a strong magnetic moment. And these material in the 3D limit, they were studied in the 80s in the bulk form. And already they showed a complex spin texture. So now the question is, what happens in the monolayer limit? Thanks so much. Thanks.
Ne approfitto per dire che qui c'è il foglio alternativo
Okay, yeah, thanks so much. Okay, so the basic way in which we model a spin material is through Heisenberg Hamiltonian. So we have connection between spin on side I and spin on side J, and then we can evaluate either with first principle or also with experimentally with neutron diffraction the way they interact through an exchange, so-called exchange coupling. And so, before getting to the results, I need to introduce another ingredient, frustration. So what is frustration in your life, right? Frustration, you're a frustrated person if you can't, satisfy all your needs. And so frustrated material is something similar. In which sense? So assume, for example, you have a triangle with an exchange interaction that wants to favor anti-aligned spins. So you place your two spin, and this interaction is happy, but then the third spin doesn't know what to do, right? If it, lines up, this interaction is not happy, whereas this one is. If you place it down, this interaction is happy, but this one is not. So what the system does is a kind of, compromise situation in which it's fairly happy, and it rotated by 120 degrees. So exchange frustration is a very nice ingredient that can give rise to non-collinear spin configuration. So if your lattice is such that it allows exchange frustration, then it has the necessary ingredient for non-collinearity or non-coplanarity to develop. So even if you have a simple, spin chain with first nearest neighbor, which is small, and second nearest neighbor, which is large and anti-ferromagnetic, then the ground state is a spiral. So, okay, this I guess I can skip. There's a big community of density functional theorists here in the audience and in the department, and so I guess I can, skip this. But by density functional theory, you can estimate from first principle the exchange interaction, which is what we did for nickel I2. And so if we do that for nickel I2, what do we get? So you have a strong ferromagnetic first nearest neighbor J, a negligible second nearest neighbor, and a strongly anti-ferromagnetic J3. And I have a triangular lattice. So nickel I2 has a triangular lattice. So now let's try to, place our spin so that they satisfy this interaction. So my first J1 is ferromagnetic. So I place my first shell to be up. Then I have a strong anti-ferromagnetic J3, and so I place them down. But you immediately see that then this interaction is not happy, right? Because this one would like to be ferromagnetic. So you have exchange frustration. And so you expect non-collinearity, right? You have a system that cannot satisfy all the exchange interaction at play. And so the fact that from exchange constant, you can basically predict some non-collinearity is part of the strength, let's say, of DFT, and even more by mapping your Hamiltonian, by your total energy into a spin Heisenberg Hamiltonian, and doing Monte Carlo simulation, you can infer that the Curie temperature is again order of, 30 Kelvin or so, and you can see that there's a spiral. And so in particular, it's a peculiar spiral called spin helix. So it's like a helix, like a staircase in your home. So from spin to spin, from side to side, the spin rotates, like in a staircase, this one. And so I have the ingredients in nickel I2 to have the complex magnetism. So the question to the answer to the first question is yes, I can have an exotic spin texture in 2D. Second question, is this kind of exotic spin texture inducing ferroelectricity. So can I have multiferroicity in nickel I2? And so in this, this was the question we asked in collaboration with my collaborator at MIT, Riccardo Comin. He's an experimental professor. And so Riccardo grew an exfoliated nickel I2, and then they did many kinds of characterization, including optical one and nonlinear optical one. So in particular, they did second harmonic generation and optical birefringence for few layers, let's say 1 layer, 2 layer, 3 layer, 4 layer of nickel I2. And so from that, results, they could tell us that there's a signal, there's a signal that emerges below a certain temperature. You see, this temperature is reduced if you go from 4 layer to 1 layer, but even at the monolayer level, you still have some kind of ordering developing. And so still at the monolayer level, the system kinds of order, and additionally, they did a symmetry analysis, and they could tell us that there's a twofold axis here. So twofold, so we have a triangular lattice. So we have a threefold symmetry. But they could tell us that there's a twofold axis. It means that the symmetry is reduced below the ordering temperature. And so from this, we inferred that the fact that you have a twofold axis is consistent with the kind of spin helix that we predicted. Additional step. Given that you have a spin helix, is this ferroelectric? And with this, we calculated basically the electric dipole that arises from two spin being non-collinear. So if I have two spin that are non-collinear, does it give rise to a dipole moment? And so this you can also estimate by first principle. You can estimate this kind of magnetoelectric tensor. And so again, the effects are small, right? You shouldn't expect strong effects here because it's the spin that produces ferroelectricity. But still, you can expect some polarization emerging from the helix. And so again, you can do Monte Carlo and see that below Monte Carlo to go to finite temperature range, and you can see that below the Néel ordering temperature, you have the emergence of ferroelectric polarization given by the spin helix. And this was, Riccardo succeeded to measure this small polarization, and so the results were in excellent agreement with our theoretical prediction. And so the answer to the second question, can the spin texture induce ferroelectricity in nickel I2, is again yes. Third and last part. So is this exotic spin texture inducing spin splitting? And can we control with an electric field? And this was what motivated our very recent work, again in collaboration with Riccardo, who's fantastic collaborator, the dream of every theorist. What did we do? So basically, there are several, things that I will not discuss. What is a P-wave magnet? But let me frame the general field. And this is connected to altermagnetism. So just to give you a flavor of how altermagnetism is becoming important, let me just tell you that it was included. So Science every year, Science Journal, every year selects 10 best topics or best discoveries, including HIV medicine or rocket landing. And last year, among these 10 best discovery, they included altermagnetism. And altermagnetism was discovered in Germany and Prague, by groups in Germany and Prague. But then yeah, we kind of worked and got to the general press. So let me just tell you what is an altermagnet. So if I look at the electronic structure of a ferromagnet, your bands are split. So you have there's, let's say, iron. So you have spin ordering, right, in your real space. And in reciprocal space, your band structure are split, right? There's one for spin up and one for spin down. So by this, you can build spin current, and so the bands, the spin split bands, give then rise to basically all applications of spintronic, which are ultimately based on spin currents. An antiferromagnet as what? As in real space, you have like up and down. But in reciprocal space, the electronic structure of an antiferromagnet doesn't show spin split band. The up and down parabola or bands are overlapped. So an altermagnet is something in between. So it's something that overall has no net magnetization. So it's an antiferromagnet. So if you measure the magnetization over temperature, you see nothing. It's an antiferromagnet. But then, if you look at the band structure, there's a spin splitting. So along certain direction, you have bands that have spin up and bands that have spin down. And so you can basically generate spin current or effects related to spin current in an altermagnet. So it's kind of in between and takes the best of both worlds, generating spin current, but also without, stray fields that affect, the miniaturization for a ferromagnet. And, but they also, kind of are antiferromagnets. So in general they are in between. And these were proposed to be collinear. Then we extended, let's say, the way altermagnetism are defined to a non-collinear magnet. And so, what is the catch here? It's a bit technical, so I will not discuss it in detail. But let's see. So I told you so far that a spin spiral generates P up. It generates ferroelectric polarization with a certain direction. And then I switch chirality, and I generate the opposite polarization. So that is the multiferroicity of nickel I2. Now it turns out that the nickel I2, based on these properties, on the symmetry properties, is such that it produces also a spin splitting. So despite being an antiferromagnet, the band structure is split. So for example, okay, that's schematic, right? But if you plot the band structure along a direction, in reciprocal case, which is parallel to the propagation vector of the helix, you basically have a spin splitting here. You see blue, for example, is spin up and orange is spin down. And if you apply an electric field by which you switch the spin chirality, the spin splitting will also revert. So you see here that orange is lying upwards with respect to blue one, but if you switch the spin chirality, then blue one is lying higher than orange one. So by applying an electric field, you're able to control the spin texture. So that was, symmetry prediction, and we sort of verified with DFT. So, okay, again, it's band structure with many directions, but let's just, for example, look at this one. So this is the band structure along a certain gamma y direction parallel to the propagation vector of the helix, and you see that the spin expectation value of your state for certain n and k has, let's say, positive spin along z on this band and negative one here. And that, so there's a spin splitting, which, yeah, for its origin is also non-relativistic. But then the nice thing is if you switch the electric field, if you apply an electric field and switch ferroelectric polarization, then we know it switches the chirality. But because you switch the chirality, you also switch the spin texture. So for example, here I cut, my band structure at a certain energy, whatever, and you see here that I have this one is orange and this one is blue. But if I switch the chirality of the spins, this one is blue and this one is orange. So basically, by an electric field, I'm able to control the spin-related degrees of freedom, which is, again, I told you in the beginning, is one of the dreams of spintronics, controlling with an electric field the spin splitting. Okay, let me get to the final slide. So I told you that we can play Lego with this 2D material, and started all with graphene, and then 2D magnets were introduced, also 2D ferroelectric were introduced, but now we have a P-wave multiferroic that we can play with. And with this, I would like to close and thank you for your attention.
Thank you very much, Silvia. Really? But I'm loud. So any question, Gianfranco, and then Sam. You're not loud. So.
Non so, ho detto che si aggiunge questa cosa qua, però mi pare che non sa.
Sì, sì. Aspetta. Sì.
Ah, sì, sì.
Gianfranco.
Yeah, first of all, thank you very much for this fascinating talk and results. I have actually two questions, if I may. The first one is very fundamentally, you showed very nicely this effect in ferroelectrics where the cation, the p cation, for instance, in the perovskite, it moves out of the center. And this is the origin of the dipole and the dipole lines, and you have a ferroelectric material. Now, my question is, the total energy of a system when you display the atom from the center of the octahedron is lower than when the cation is in the center of the octahedron, right? So when you break the symmetry, you gain energy.
Sorry?
The total energy. I mean, you have shown this curve where basically you have a lower energy
when you
where the cation is displaced.
Yes.
Okay, is this a local phenomenon? So if you have just one octahedron and you just display one cation, is this a lower energy? And if yes, why?
Okay, so so how would you do that? So let's say that ferroelectricity is a cooperative phenomenon, right? So once I create a displacive, in this cation, then also this one will be affected. So let's say if I don't know how to simulate the total energy of just one octahedron. So would you like kind of
with DFT you can
one?
do that if you have a relatively large supercell. If you have enough larger supercell, you have no.
Okay, so you would, say like a supercell of, centrosymmetric octahedra, and then you would just displace one, let's say,
exactly.
in the center.
Yeah.
This is a good question. I cannot answer. But probably you have a lowering of the total energy still, but I don't know. I don't know because that's not periodic. Yeah.
Yeah, first of all, I would like to know if it is, because that is the difference between a local effect. So is first the eggs of a chicken is always the question.
Right.
So is the dipole that when you align, or
so
is
I would
it collective?
say that, you would, so in the density of state, let's say, when you plot the density of state of titanium and oxygen in the paraelectric one, they are at a certain energy. And then if they displace, they go to lower energy. And I would say that this effect, the DOS, is pretty local. I wouldn't, and so you gain, let's say, eigenvalues energy, right, coming from just the sum of eigenvalues. So it's a kind of, I would say, but yeah, I didn't do the simulation, so it's better not to.
Yeah, well, it's interesting because this reminds me that in zeolites, you have zeolites.
Okay.
You have these porous materials.
Right.
You have these cavities or hexagons, and you have cations in zeolites. The cations are not in the center of the hexagons.
Right.
The cations are slightly off center.
Right.
And that is because there is more space for the cation, and the same is basically in perovskite. So I would be interested to know if it is a similar phenomenon. Okay.
So yeah, it depends on whether it's a size effect also, but I don't think in barium titan you have a size effect, right? Then it's predominantly really hybridization. But okay, we can discuss later.
Second question is quicker. I mean, the exchange coupling in magnetic materials is strongly dependent on the functional in DFT that you're using. So which kind of functional do you need for these high, accurate results?
Sure. So yeah, that's a good question, of course. We generally do DFT plus U. So we just add, to standard LDA or GGA. Of course, if you change the U, the quantitative value of the exchange coupling will change. But then the physics, let's say, will not change in the sense that, for example, we checked, the J3 over J1 ratio that, in the end determines the fact that you have a helix or not. And this is not that dependent on you. But of course, it's a question. How to estimate our, ways of proceeding is very, let's say, pragmatic, I would say. So we just change the U and see. Sometimes we see, things qualitatively changing. And then, of course, we cannot make any prediction. In these cases in which, of course, quantitatively, everything will change. But then qualitatively, the ground state will not change. And the Curie temperature, it oscillates a bit, but not that much. Then we can safely predict, right, that the system will have a spiral. But of course, it's a difficult question. I don't think there's a gold standard. I don't know, in chemistry, maybe you have a gold standard to follow. But we don't, right? If you do the MFT, you maybe for insulator that's a bit better, but who knows? And then DFT plus U and also hybrid and it's a question, right? And hybrid, sometimes right? You predict the good structure, but then the wrong exchange, or the other, for another you have the other way. So it's a, difficult, answer to give.
So thank you very much for a very nice and complex presentation. I also have two questions. First of all, one more practical. Ferroelectric materials, very interesting for application that combine a lot of properties, but the problem is the temperature of application and problem with stability, with percentage of polarization, etc. So do you have some suggestion how, for example, nickel IO2 can be applied, can integrate in real microelectronics? Because it's not so trivial question.
Right. Yeah, you mean using this spin-related mechanism? Yeah, that's a, I would say. So, the thing is that frustration, so everything comes from exchange frustration, right? Which automatically brings your temperature down. And so, but of course, if you start from very high J's, like in nickelates and cuprates, then you have frustration, but still your exchange coupling is so strong that you can reach so I think, that you have hexaferrite, very complex one, which we never tackle because they have huge, supercell, but there I think you can reach room temperature, right? But of course, I don't know how, ferrites with, unimaginable chemical formulas can be well integrated into electronics.
Maybe some heterostructures, combine some
let's say I would say the way to integration, the road to integration with microelectronics is still long.
And second question, possible. About chirality. For example, magnetic chirality based on the Zaleshinsky-Mori interaction. For that reason, we have very nice spin texture like solitons, fermions. That's very interesting for magnetic memory device. But the question is, it possible to tune, to control the magnetic chirality in this type of materials by electric field?
Say it again. The question is
About fermions, solitons, some.
to control with an electric field. Oh yes, not okay. Yeah, that's a good question, and we worked on that. Not on nickel I2. So nickel I2 is centrosymmetric, right? So even if you let's say Zaleshinsky-Mori is not allowed by symmetry. So the non-collinearity that you see is only driven by exchange frustration and not by DM. But let's say there are other materials in which you're allowed to have Zaleshinsky-Mori, and I think, so of course, depending on which, skirmion you have and which kind of, topological charge you have, but we discovered actually that there are some topological texture that have a dipole. Right? And of course, if they give rise to dipole, then they can be switched with an electric field. That is, we are going to publish it soon. So we did like chromium I3. We started actually with domain walls, and we discovered that domain wall can actually give rise to a ferroelectric dipole. And so in principle, with the tip, right, you could move the domain wall. And then we thought, okay, but the domain wall is just, one direction, and then we can make it like, isotropic in space, so it's like we have a skyrmion in the end, right? So there are some skyrmion that have a dipole. And but that's theoretical, I'm not sure. Yeah.
Let's hope.
Yeah.
Thank you.
Okay. Any other question? Okay. Then somebody else has to handle the microphone because I have to go teaching.
Okay, just a clarification. Maybe you mentioned that I simply missed the point. In the altermagnet investigations, when you have the spin waves, do they...
That's electronic. That's electronic states. It's not spin.
That belongs to mobile charges, or is it due to the localized magnetic moments?
Okay.
Because you said, in spintronic, in the end, anything boils down to spin currents.
Yes.
But if that does not pertain to spin current, then you have to take into account exchange between mobile carriers as well as...
Right. Okay. Yeah. I shouldn't have said that everything belongs to... spintronics is based on spin current because I work only on insulator, right? But okay. Let's say in general, of course, you need a metal, right? So spintronic is true that, generally it's most of spintronic applications are based on spin current. That you can think of, doping the material and then having spin current. Let's say that's my excuse. So now, okay, what is the question here, right? Let's say here, these are electronic states. These are not magnon. These are not spin excitation, right? So let's say the question is, for example, okay, here I have a Fermi level, which is, it's a semiconductor. But assume now I dope my material and my Fermi level is here. And then if I run a current, let's say, left, or if I run a current right, then my spin expectation value should be different, right? And this is one possible way, right? That I switch, and I apply electric field and I switch, right? So the current that had spin up, now a spin down. That is the idea. But of course, your Fermi level is far, I don't know. It's, again, also we are not, I skipped on that, but let's say, Ricardo sees a very complex spin texture. So he's a helix, but it's like 7, close to 7 unit cell, maybe incommensurate, so we don't know the pitch, and so we did like a model material. So here is like 3 unit cell with spin cycling, so we are not even completely sure that this is the real band structure. But if it were, let's say, and you dope your material and your Fermi level is here, and you just have, current in this direction. So it's very many approximation. Then that would be the way to use it, right? Switch the spin expectation value, so switch a spin current by, applying an electric field.
So is there any similarity with Rashba-induced spin splitting?
That's a very good question.
This is non-relativistic, you mentioned?
Yeah, it's not relative. So I'm a fan of spin-orbit coupling, and I work on every aspect of spin-orbit coupling. But the catch of altermagnetism and the way they sell it is that it's non-relativistic. Right? And this is the non-relativistic band structure. So if I see a spin splitting here, it cannot come from spin-orbit coupling. We thought, okay, it's iodine, then spin-orbit coupling will change the situation, but actually it doesn't, right? You have small modification. So in terms of Rashba, of course, the microscopic origin is different. For Rashba, you need spin-orbit coupling. Let's say you still have an odd in K. You have an odd in K splitting, right? And that's the same as the one you have in Rashba. But the microscopic origin is different.
Thank you.
Are there any other questions?
So I have time to just close with packing. So thanks a lot for coming. Thanks a lot for Silvia Picozzi for giving this fantastic talk. And when is next one, Director? You know it already? Or? Okay, so we have time for the next one. I hope to see you all for the next breakthrough in material science. Thank you. Già che siete, scusate. Sì. Già che siete qui, vi ricordo che il 25 e il 26 abbiamo le presentazioni di fine anno degli studenti, che quest'anno, dei PhD students, che quest'anno hanno questo formato un po' workshop, domani e dopodomani anche. Sì, esattamente, sono tutto il giorno, ci sono sul sito del Dipartimento tutte gli orari.
Molto poco, no.